It's amazing to think about how the early universe was like this giant cosmic fog
Yeah.
for hundreds of millions of years after the Big Bang, right?
Yeah.
All this neutral gas just like absorbing UV light and making it super tough to see anything.
It was a real challenge, you know?
For sure. But the stuff you sent me, it's like new
Yeah.
findings from the James Webb Space Telescope are suggesting that that fog might have started lifting way earlier than we initially thought.
Oh, absolutely. Yeah.
Really?
Yeah. This opacity has always been like a massive obstacle for astronomers trying to study the universe's earliest phases, right?
Right.
I mean, those first galaxies, they hold like the key to understanding how everything began, but they're largely hidden because their light, which is mostly UV, couldn't travel freely through space.
I see. So it's like trying to listen to someone whisper from across a really noisy room.
Exactly,
You
yeah.
just can't make it out.
Yeah, and so, well, this new discovery, it seems like that whisper might have gotten a little bit clearer and much sooner than anyone expected.
So tell me more about this discovery. What's got everyone so excited?
Okay, so basically there's this report published in Nature about this galaxy, and get this, it formed just 330 million years after the Big Bang.
Wow, that's incredibly early.
Super early, and what's even cooler is that it seems to be surrounded by this bubble of transparent ionized gas.
Oh, wow. So like a little clearing in the middle of all that fog.
Precisely, yeah.
Okay, so today we're diving deep into what this discovery means, right?
Yeah.
Like how does this early galaxy, this clear bubble around it, help us understand how the universe went from opaque to
Right.
transparent, that big transformation?
Exactly. We're going to unpack this finding and, yeah, make sense of what it tells us about the cosmos way back then when things were so different.
Okay, so let's rewind a bit. I'm still a little fuzzy on why the early universe was so foggy to begin with. Can you break that down for me again?
Yeah, so remember all that neutral gas we talked about? It was mostly hydrogen, just floating around after the Big Bang. And these early galaxies, they were bursting with energy, radiating tons of UV light.
Right. The newborn galaxies shining bright.
Exactly, but it's like they were behind this super thick curtain, you know? The neutral gas was insanely good at absorbing that high energy UV light.
So even with like a crazy powerful telescope, we wouldn't have seen them back then.
Nope, their UV emissions would have been completely blocked, like trying to see sunlight through a brick wall.
Got it. So that's why peering back to that era is so hard for astronomers.
Absolutely. We're talking about a time when the universe was still figuring itself out, like the very beginning.
Right, but amidst all that chaos, galaxies still formed.
Oh, yeah. Gravity did its thing, pulling together massive clouds of that primordial gas, and boom, the first stars ignited inside them.
And we're not just talking about old galaxies, right? Astronomers have found some that formed ridiculously early.
Oh, yeah, less than 300 million years after the Big Bang.
Wow, that's like a blink of an eye in cosmic terms.
Seriously, and this galaxy, JD's GSZ131, it's a prime example.
Jade's GSZ131.
Yeah, its light started traveling towards us when the universe was just 330 million years old.
So that light has been on a 13.5 billion year journey to reach the James Webb Telescope.
That's right, and that ancient light gives us like a snapshot, a peek into the conditions of the very early universe.
It's mind-blowing.
And remember how we said neutral gas was blocking all that UV light? Well, something major shifted. Like, the universe went through this transformation from neutral to ionized.
Okay, so this reionization thing, that's where the change happens, right?
Exactly. That's the process that made the universe transparent.
But how does it work? I mean, what happens when all that UV radiation from the galaxies meets the neutral hydrogen?
Okay, so picture this. UV photons, these tiny particles of light, are hitting the hydrogen atoms, right?
Oh, yeah.
And they're so energetic that they knock electrons off those atoms.
And that creates ions.
Exactly. Atoms with an electric charge. And as more and more UV light floods the universe, more and more hydrogen gets ionized.
So the hydrogen loses its electron and can't absorb UV light anymore.
Precisely, the gas becomes transparent, like it can't block the UV light anymore.
So it's like these early galaxies were slowly clearing the fog around them, making little pockets of see-through space.
Yeah, that's a great way to think about it.
And this reionization, like when did it start? How long did it take? What caused it? That's all still a bit of a mystery, right?
Totally. Yeah, figuring out the specifics of reionization has been a huge puzzle for cosmologists.
Mhm.
The prevailing idea was that it kicked off around 500 million years after the Big Bang and took another 500 million years to finish.
Okay, so a long process.
Yeah, but this new study, based on what you shared with me, it's suggesting that reionization might have started much earlier.
Really?
Yeah.
Way earlier than 500 million years.
It seems so.
Tell me more about these astronomers and what they found about Jade's GSZ 13.1.
Okay, so a team from the Cosmic Dawn Center in Copenhagen, they were studying this super distant galaxy,
Right.
and they made this incredible observation. They detected light from Jade's GSZ 13.1 at a specific UV wavelength called Lyman-alpha.
Lyman-alpha. That sounds familiar. Didn't we talk about that before?
Yeah, it's a wavelength that gets easily absorbed by neutral hydrogen, making it a perfect tool to study the universe's transparency.
Okay, so remind me, why is finding Lyman-alpha light such a big deal when we're talking about a foggy early universe?
Well, because of its short wavelength, Lyman-alpha is incredibly sensitive to neutral hydrogen.
Right.
So the thinking was that we shouldn't be able to see it from any galaxy that existed when the universe was less than, like, 500 million years old.
Because of all that gas blocking it.
Exactly. It just wouldn't get through.
So the fact they found it coming from Jade's GSZ 13.1, which formed even earlier, that's the shocker, isn't it?
Huge shocker. Yeah, it's like Joris Wittstock, the lead researcher, said, and I quote, "Young galaxies shine brightest at a very specific wavelength of light, originating from hydrogen. To astronomers, this light goes under the name Lyman-alpha. Because of its short UV wavelength, it is easily absorbed by the surrounding medium, and therefore no galaxy from when the universe was less than 500 million years old has showed us this particular kind of light."
Wow, so their finding is, like, turning our understanding of the early universe upside down.
Pretty much, yeah.
Okay, so if this Lyman-alpha light managed to travel all this way to the Webb telescope, it means there had to be some clear patches around that galaxy, right?
Yeah.
Is that where those cosmic bubbles come in?
You got it. That's the idea.
So how do those bubbles form?
The theory is that those early galaxies, with all their energy, weren't just sitting there. They were actively, like, frying the neutral hydrogen around them with their intense UV radiation.
So they carved out these little zones of ionized gas.
Exactly. And within those bubbles, the gas was transparent, allowing light, including Lyman-alpha, to travel freely.
Okay, so the Lyman-alpha light from Jade's GSZ 13.1 escaped because it was inside one of these ionized bubbles.
That's the leading hypothesis, yeah.
And over time, these bubbles grew bigger and bigger, eventually merging to fully reionize the universe.
Precisely. And finding Lyman-alpha from this early galaxy, it's like a smoking gun.
It's proof those bubbles existed.
Exactly. It's like Wittstock said, and I'm paraphrasing here, but he basically said that from theories, simulations, and observations of later epochs, we know that the most energetic UV light from galaxies essentially fries the surrounding neutral gas, creating bubbles of ionized, transparent gas around them.
And they think they found one of the first of these bubbles.
That's what it looks like, yeah.
It's pretty wild to think about these little clearings popping up so early in the universe.
I know, right? And none of this would be possible without the James Webb Space Telescope.
Oh, absolutely. It's like having this brand new window into the universe's earliest moments.
It's amazing. Webb's sensitivity, especially to infrared light, and its ability to analyze light wavelength by wavelength, that's what made this discovery possible.
Incredible.
It's like Peter Jacobson, a scientist working on Webb, said, "We knew we'd find some of the most distant galaxies when we built Webb, but we could only dream of one day being able to probe them in such detail that we can now see directly how they affect the whole universe."
And it's just getting started, right?
Mhm.
I mean, who knows what else Webb will reveal?
Right.
So we've got this early galaxy, JD's GSZ 13.1, and it's got this bubble of ionized gas around it.
Mm-hmm.
What could have caused that? Was it just the galaxy itself, or is there something else going on?
Well, there are a couple of main ideas, right?
Okay.
One is that the very first stars, they were different from the stars we see today.
How so?
They were much hotter, much bigger, and as a result, they were blazing with UV light.
Ah, so these super bright first-generation stars, they could have been the ones clearing the fog.
That's one possibility, but there's another really interesting one.
Okay, tell me.
Supermassive black holes, you know?
And the centers of galaxies.
Yeah, and we know many galaxies, even early ones, had them.
Okay.
As these black holes gobble up gas, it gets heated to millions of degrees, and that makes it shine brightly in X-rays and UV light.
Ah, so that could have caused the bubbles too.
Exactly. It's like Wittstock said, most galaxies are known to host a central supermassive black hole. As these monsters engulf surrounding gas, the gas is heated to millions of degrees, making it shine brightly in X-rays and UV before disappearing forever. This is another viable cause of the bubbles, which we will now investigate.
So it's either The first stars or the black holes, or maybe even a combination of both.
Could be, yeah, that's what they're trying to figure out.
Fascinating, these cosmic powerhouses shaping the early universe.
I know, it's amazing.
And you sent me this image too, right? What does it show?
Oh, yeah, it's really cool. It shows like a wide view with about 10,000 galaxies, all seen by the James Webb.
Wow, 10,000 galaxies.
Yeah, and then it zooms in on Jade's GS-Z13-, which just looks like a faint red dot at the center.
Wow, that really puts things in perspective.
It does, and the credit for the image goes to NASA, ESA, CSA, and the JADES collaboration, including Woodstock and Jacobson.
Okay.
And then there's this panel showing JADES GS-Z13-1 as seen through 7 different filters.
Filters. Like on Instagram.
Not quite. Each filter is sensitive to a specific range of wavelengths, from UV on one end to longer wavelengths on the other.
Okay, so what does that tell us?
Well, you can see that the galaxy is completely invisible in the most UV filters.
Because of the neutral gas blocking the light.
Exactly, but as you move towards the longer wavelengths, it becomes more and more visible until you get to the last 4 images where it's clearly there.
Oh, wow. So it's like a visual demonstration of how the early universe was opaque and how Webb is helping us overcome that.
Precisely.
That's really amazing.
Yeah, it really highlights how challenging it was to observe these early galaxies before Webb.
Right, and the fact that it's invisible in the UV, which is the very light it's emitting, that's so counterintuitive.
I know, but that's the early universe for you.
Okay, so big picture. What's the main takeaway from all this? Like, what does this discovery tell us about the early universe that we didn't know before?
Well, it seems like the epoch of reionization, that time when the universe went from opaque to transparent, it might have started way earlier than we thought.
Like how much earlier?
The Lyman-alpha from JADES Z13-1, which existed just 330 million years after the Big Bang, it suggests that ionization was already happening.
So those bubbles of clarity were forming much earlier.
Yeah, and it basically pushes back our timeline for when the universe started becoming the transparent place we see today.
And none of this would have been possible without the James Webb Space Telescope.
No way. Webb is revolutionizing our understanding of the early universe.
It really makes you wonder, like, what else is out there? Could those early bubbles tell us even more? Like, about the distribution of the first galaxies, or even about the very first stars and black holes?
That's a great question. Those early bubbles are like remnants of the universe's first light sources, and by studying them, we might uncover some incredible secrets about the formation of the earliest cosmic structures.
Wow, and with Webb just getting started, who knows what other discoveries await us?
Right. It's an exciting time to be studying the cosmos.
Absolutely. And for anyone who wants to dig even deeper into this research, be sure to check out the Nature paper by Woodstock and his colleagues from 2025.
Good idea.
We'll include the DOI, which is 10.1038 S4 round 586 025 0877995, in the show notes.
Perfect.
It's a fascinating read, definitely worth checking out.
Agreed.
Well, this has been an amazing deep dive. I can't wait to see what other secrets the early universe reveals.
Me too. It's an incredible time for discovery.
Until next time.
Take care.
Bye-bye.